Testing. Testing. Testing, testing, testing. Testing. Testing, testing. Testing, testing, testing. Testing, testing, testing. All right, I think we're good to go. Testing. Testing. Testing, testing. All right. Testing, testing. We are live. Welcome to another Hoopo stream. Today we are going to be looking at a paper called Toolformer. This is language models can teach themselves to use tools. This is a paper that's coming out 9 February 2023, which is relatively recent, coming out of a academic group, I don't know where that is, and Meta AI Research. So kind of joint work between Meta and this university lab, and it's called Toolformer. It seems to be getting some hype. It's on the machine learning subreddits. It's popped up a couple times, and it's interesting because you have basically a large language model that is using different APIs as if it was tools, right? So it's kind of a form of tool use. So let's see if the hype is warranted. Let's see what this paper's about. Language models, LMs, and large language models, LLMs, exhibit remarkable abilities to solve new tasks from just a few examples or textual instructions, especially with scale. They also paradoxically struggle with basic functionalities such as arithmetic or factual lookup. Isn't this also the case with humans? Right? What does that mean? Where much simpler and smaller models excel. In this paper, we show that LMs can teach themselves to use external tools via simple APIs to achieve the best of both worlds. Let's make my face a little bit less big. I feel like it doesn't need to be that big. We introduce Toolformer, okay, a model trained to decide which APIs to call, when to call them, what arguments to pass, and how to best incorporate the results into future token prediction. So there you go. I think that's pretty much the TLDR for the whole paper. Is that the action space of this LLM is not just producing word tokens, it's also optionally calling specific APIs. So it'll be interesting to see how they actually implement that. This is done in a self-supervised way, requiring nothing more than a handful of demonstrations for each API. Okay, that's important. So you have a kind of a supervised learning data set. We incorporate a range of tools, including a calculator, a QA system, a search engine, a translation system, and a calendar. Toolformer achieves substantially improved zero-shot performance across a variety of downstream tasks, often competitive with larger models, without sacrificing its core language modeling abilities. Okay, LLMs achieve impressive zero and few-shot results on a variety of language processing tasks. They have shown several emergent capabilities. They have limitations of up-to-date information. This is another interesting problem that I don't know how they're going to solve, but all these companies that are offering a big LLM, such as ChatGPT, they're going to have to figure out some way to kind of retrain it, perhaps even daily, right? So that it has the most recent news and recent events. I doubt they'll be retraining the entire thing. I don't know how exactly they're going to implement that, but keeping these LLMs up to date is definitely an interesting problem to look forward to in the future. Difficulties understanding low resource languages, lack of mathematical skills, unawareness of the progression of time. Simple way to overcome these tools or overcome these limitations is the ability to use external tools, such as search engines, calculators, calendars. There's other use for search engine lookup. People really want this for LLMs so they can reference their work. I've seen a couple papers where people are basically trying to do that, where they want to be able to get the LLM to answer a question, but then also cite the sources in its library, I guess, in some kind of index as to which thing is the closest to it. Hindering a more widespread adoption, we propose Toolformer, a model that learns to use tools. Okay, so here you have the bulleted points here in the introduction, which usually basically summarize for you the novelty and contribution of this paper. The use of tools should be learned in a self-supervised way without requiring large amounts of human annotations. Okay, so they did say that they have requiring more than a handful of demonstrations, so they are collecting a data set for each API, and I wonder how they create that in such a way that they don't need a ton of human annotations. The LM should not lose any of its generality and should be able to decide for itself when and how to use which tool. In contrast to existing approaches, this enables a much more comprehensive use of tools. Our approach to achieving these goals is based on the recent idea of using large language models with in-context learning. Okay. To generate entire data sets from scratch. Given just a handful of human written examples of how an API can use, we can let an LM annotate a huge language modeling data set with potential API tasks. Okay, so this is how they're doing it. They're basically doing like a kind of auto labeling, or more generally, they're synthetically generating a data set for API use. So they're using a learning model to create a data set of how to use API calls and then training on that data set. So there's a lot of different potential problems you could be introducing with this, especially if you're using the same language model to generate the data set that you are used to train the data set. But we'll see how they answer these, or they address these challenges. We use a self-supervised loss to determine which of these API calls can actually help the model. Finally, we fine-tune the LM itself on the API calls that it considers useful. As illustrated in Figure 1, through the simple approach, LMs can learn to control a variety of tools and choose for themselves which tool and when to use and how. So one thing that's kind of annoying me here is they keep changing the wording here. They're calling it large LMs, and then here they called it large language models. And then here they just say language models. So at the end of the day, every single one of the models here is a large language model, which is an LLM. You know, there isn't a specific cutoff point for the L in LLM. And I would say all of these count as large language models. So a little bit of notational consistency there would have been useful. Approach is agnostic of the dataset being used. We can apply it to the exact same dataset that it was used to pre-train a model in the first place. This ensures that the model does not lose any of its generality and language modeling abilities. Okay, so they actually generate the synthetic data from the exact data it was trained on. Toolformer, which is based on a pre-trained GPT-J model with 6.7 billion parameters. So this isn't necessarily absolutely massive, but it is big. And it outperforms a larger GPT-3 model on probably some specific benchmarks, like, I don't know, some kind of math benchmark, something where it needs to get the answer right every time. Okay, approach. Our aim is to equip a language model M. So let's start getting out our notation color here. We use green to highlight mathematical definitions of terms, so we can keep track of them. So language model here is going to be M, capital M. with the ability to use different tools by means of API calls. So, let's just quickly get on this tube here. This allows seamless insertion of API calls into any given text using special tokens to mark the start and the end of such a call. Okay, so we were asking the question, how are they going to actually implement an additional action, right, that the LLM can take, which involves calling an external API? And in reinforcement learning, right, you might have a discrete set of actions that you can take at every step. And each of those actions might be represented as maybe like a one-hot vector, right, where you have 10 possible choices to do. But these language models, the way that they're architected, the output space, right, the output of the language model is just a token. It's like a word token, right? And usually those tokens represent different parts of words, and they're limited to words and text and sequences. But what they're going to do here is they're going to create a special token, a new token that, I don't know, maybe it's all zeros, maybe it's like some weird part of the embedding space that it doesn't have other tokens in it. I don't know how they guarantee that this token has kind of uniqueness. But they're going to decide that these two special, they're going to make these special tokens to mark the start and the end of the API calls. So that's how they're going to actually implement this. We represent each API call as a tuple. Okay, so tuple just means two things. Right, so you have two things here. You have AC and IC. AC is the name of the API. Okay. So there's some limited number of these, and IC is the corresponding input, so it's probably just one-hots, I assume. Given an API call C with a corresponding result R. Okay, so C is the actual call itself, and then R is the result of the API call. We denote the linearized sequences of the API call, not including and including its result, respectively, as EC equals API. So this is the token here. So this token that we were hearing about here, using special tokens to mark the start and the end of such a call, that's these tokens here. So they're kind of using this almost like an HTML style like form, like call here, where HTML, which is like a web programming language, you do like blocks of code, for example, and the way you like here, it's probably easier just to show you, but in HTML code, right, you might have, for example, here, this is what the website looks like. You'll have the body of a text, and then once this part of the body is over, you'll have /body, right? Or maybe you have a paragraph and you'll say beginning of paragraph and then /end of paragraph. So they've adopted kind of a similar style of saying this is the beginning of the API and this is the end of the API. So I kind of like that. The special tokens are created in text space, and then they're just converted into tokens rather than coming up with some specific point in token space, which is another way they could have done it. But either way, here you have the actual API call itself. AC is the name of the API, so this is like each API is going to be kind of like a function if you think about it. So you have to decide what's the input to my function and then what's the actual function that I'm using. Okay, there's actually an additional special token here. This one here, this arrow, which I guess is a way to link an output. So if your API call involves returning some kind of output, maybe a reference or something like that, or the number in a calculation, you can give this token as well. Given a data set, okay, so we have our data set here of plain texts. We first convert this data set into a data set of augmented, so this is the augmented data set, right, where they're going to use an LLM to basically create this augmented data set or a synthetic data set. I like augmented I think that's a good way to describe it. It's very similar to augmentation in other domains where you might take an image and then you might copy paste I don't know, pictures of dog on this image, right? It's called cut paste augmentation. Let's see. Yeah, something like this, right? Ooh, that picture is very small. But cut paste augmentation is hey, maybe you have some training data of these people on this field, you have some training data with giraffes. Why don't you copy paste the giraffes into the picture of the people playing soccer, and then you'll get your model will become more robust over time. So kind of a similar type of augmentation going on here, except the cutting and pasting is not happening in an image, it's happening in a sentence, right? They're adding this additional API call into the sentence. So first we exploit the in-context learning ability of M to sample a large number of potential API calls. So first thing they do is they sample a large number of these potential cut pastes in there. And they're probably going to have a high temperature when they actually do this, such that you get a kind of broad sample of potential API calls. Then they're going to execute these and finally check whether the responses are helpful. Okay, so then they have basically a filtering. So there's a bunch of different large language model stuff that uses this kind of generate and filter kind of paradigm. If I remember the LLM that solved leak code problems, I forget exactly what it was called, but there was a paper where they had an LLM solving leak code style problems, and it was a similar kind of approach where it would actually generate a large number of solutions, and then you would then filter down the solutions. So a similar kind of thing is happening here when you're generating this augmented data set, where you're generating a large number of potential API calls that are going to get put into your original data set, and then you're filtering those down. So how does the filtering happen here? After filtering, okay, they don't explain it here, but they'll probably explain it later. We merge API calls from different tools, resulting in an augmented data set, and then fine-tune M on this data set. Okay. Sampling API calls. So this is more details on how they actually sample the different API calls, right? So they probably want something broad, a broad number of different potential API calls. So let's see how they actually do that. We write a prompt. Okay, so a little bit of prompt engineering here that encourages the LM to annotate an example with API calls. Okay, so the example X is the original text, right? It's just a sequence of word tokens. Example of such a prompt is shown in figure 3. Okay, let's look at figure 3. An exemplary prompt that is used to generate API calls. So, okay, this is the prompt here. Your task is to add calls to a question answering API to a piece of text. These questions should help you get information required to complete the text. You call the API by writing QA question, where question is the question you want to ask. Here are some examples of API calls. Okay. So this is the prompt. They actually ask the LLM in kind of a standard prompt question answering kind of format. And then the LLM will actually go through and decide where to put these things. So this is still absolutely crazy that you could do this with LLMs. Like the fact that this is even possible. You can ask the LLM to annotate the data itself is kind of crazy that we're at this point, but you can see here how it's doing that. Joe Biden was born in Scranton, Pennsylvania. Joe Biden was born in QA. Where was Joe Biden born? Scranton. QA. Which state is Scranton, Pennsylvania? So it added these. And the crazy thing is you didn't tell that, there's no step where the LLM was told how to add calls to a question answering API. It somehow has some notion of what a question answering API should be and where the question answering API calls should be. So at no point did the authors of this work kind of add this functionality to a transformer. This functionality has been there since the beginning. They're just kind of using the fact that it exists. It's quite crazy, right? Coke is a carbonated soft drink, and you can see here, what is another name for Coca-Cola? Who manufactures Coca-Cola? So the LLM annotates its own data set that it then fine-tunes on. Let PM, Zn plus 1, all the way to Zn, be the probability that M assigns to token Zn plus 1. Okay, so you have your example, which here in this would be the input here. Joe Biden was born in Scranton, Pennsylvania, right? You could break up this sentence into different tokens, right? Probably one token for Joe. Pennsylvania probably broken up into multiple tokens. But those are your tokens here. X equals x1 to n. Well, actually, those are the raw words, right? So X is probably the raw text. And then the tokens are Z. So these Z's here correspond to individual parts of the original sequence. And as a language model does, what it's largely doing is it's basically giving you the next token. So given a sequence of tokens, it predicts the probability over all possible tokens of the next token, and then you just kind of can greedily pick the most probable next token. So you see here how what this language model is doing is it's basically saying, what is the n plus 1 token given all the previous n tokens? So they sample up to k candidate possibilities. So again, there's probably going to be one token that has the highest probability of being the next token. If you were to pick that token, you would be doing what's basically called greedy kind of selection, which means that you're just choosing the token with the highest probability. But in this case, right, they want to create a data set, and they want to have a variety of different tokens, a variety of different styles of this call. So they're going to pick the top k possible tokens. So every time that the model goes to pick a token, it's going to pick the top k, and they're going to have k of these potential calls. So all you see here is probability M. M is the language model, so the language model gives you a probability I for each potential position here within the sequence. Here you have the input, right? Every part of the input from the first index of the input all the way to the index right before the one that you are trying to calculate. So all of the beginning, if you're going from here, Joe Biden was born in, this would be up until this point here, right? P of X, which is just the prompt, so you're giving it the prompt and then all the tokens up until that point. And this is your start of the API token. So what is the probability that on this point right here, the next token is an API call, right? Because at some point it has to decide to interrupt these tokens and just insert one of these tokens, the beginning of the API call tokens. So this will give you the probability of the next token being the start API call token. Okay. Given a sampling threshold, all positions I. If there are more than k, we only keep the top k. Okay. All right, so basically what they described in this point here is that they can take their large language model and they can ask it at every single point along the sequence, right? At every single point along the sentence, they can say, what is the probability of the next word in the sentence or the next token of being the start API call token, right? And let's say it's reading this sentence here. It starts off at the beginning and it says, Joe, what's the probability that the next word is start token? Pretty low, right? The probability that the word is Biden is actually much higher. So it's probably a very low probability here. Maybe there's a higher probability here. So you're going to get a probability that the next word is API token for every single word in this sentence, right? Every single point in the sequence. And then they're going to say, okay, all those different points at which we could have inserted this start API call token, which one of these has the highest probability, right? And we're going to have basically some kind of threshold probability. And if the probability is above that threshold, we're going to say that is, they're also going to make sure to only have k of these. But at each of those position, they're going to say, okay, what is the API call that would make sense in that context? So this is how they decide where in the sentence they're going to pick, or they're going to put the API calls. So up until now, they're not deciding what API call to use. The only thing they're deciding is where to put the API calls, right? They're just deciding the probability of this API token of being the next token. Okay, we then obtain up to m API calls by sampling from m given the sequence. Okay. M API calls by sampling from m given the sequence this. Okay. So now that they have a bunch of positions, right, up to k positions within this sequence, within this sentence where you could put an API call, they're going to say, okay, let's assume that the API call is here. Let's give the prompt, or give the LLM a sequence that is the sentence and then the beginning API sequence. And the LLM is going to say, okay, if you give me a sentence that is Joe Biden was born in API call, what's the actual API call going to be? So this first part here, they're just deciding where in the sentence to put the API calls, and then this second part here, they're actually going to ask the LLM what is the actual API call you're going to put in there, right? Okay, as a next step, we execute all API calls generated by M to obtain the corresponding results. How this is done depends entirely on the API itself. It can involve calling another neural network, executing a Python script, or using a retrieval system to perform search over a large corpus. This is the kind of the last part here is what all these companies are working on, right? These large language models as working in tandem with kind of a retrieval system, right? And most people think that this is how you're going to get kind of better performance and better accuracy in terms of like only having truthful content and only having content that perhaps is filtered by advertisements or so on. So information retrieval systems in tandem with large language models, I think, is the future of search. So stay tuned for that. The response for each API call needs to be a single text sequence. Yeah, so this is the return. So if we remember up here when they were defining the API call, you can also produce this token here, the arrow token, and then there's going to be this R. Oh, shit. And that R simply refers to the return of the API call. Let I be the position of the API call CI in the sequence. Okay. I is just the position of the API call. Right, so we learned here that if you have a sequence from I equals 1 to n, you have to decide where to put that API call within the sequence. So the position of that API call within that sequence is simply just I. This is the sequence that we defined originally, and then RI is the response from the API. Further, given a sequence WI, I in n of weights. Okay, so now you have these weights here. I'm assuming what they're probably going to do is, yeah, weighted cross entropy loss. So they're basically, this is the same kind of loss that you would use for a classification problem, right? Where you have a variety, you have maybe a cat, dog, mouse, or something detector, and then the output of your network is going to be a one hot over those three classes, and then you would basically use something like a cross entropy loss to teach the model which class to predict. Here they're basically using it to choose which of the positions, right? The positions I within the sentence, and here you have some set of positions, right? This script n, that just means like normal numbers, so 1 to n basically. So I is, all the positions I are within that set. Log PM, so this is the probability coming out of the large language model, right? You have your actual xj, which is the token at the jth position. You have z. Where is z? If the model is prefixed with z. Do they tell us what z is? They do not. So we don't know exactly what z is just yet. They might have told us, but they might tell us in a second here. They have this here, x1. Oh, you guys can't see because my head is in the way. They have this head here, or this x1 to j minus 1. This is basically every token in the sequence before this token. So this is all the tokens before the specific token. They're conditioning the language model on this. The language model is going to give you a probability. You're going to take the log of that probability. The reason you're taking the log is just to make things look nice. Anytime you see logs, they're basically just kind of shaping probabilities to make it look nice. That's largely what kind of these cross-entropy losses are doing. There's a lot of logs, a lot of exponents in these kind of probability-based losses. They're multiplying it by this weight here, right? And then they're summing all of these together. So j equals I to n. So j here, the index that is being used over the sum here is basically just all the different positions where you could have an API call. And the result of that is the loss. So you're going to have, I guess, a different loss for each position I. We still don't know what z is. We compared two different instantiations of this loss. Okay, so there's, I guess, two different, maybe the plus minus here denote upper bound and lower bound. So they have kind of a version of this loss that is always going to be bigger than the other one. Let's see what's going on here. So E, what was E again? I thought they defined E. Okay, yeah, so E is the full call, right? The full API call. So you can have EC or you can have ECR. So this one does not have a return and this one does have a return. So API calls with and without returns. So you have here a API call with a return for the ith token, or the API call starting at the ith token position. That's the upper bound. The lower bound here, li minus, is the smaller of these two. It's either the same loss function we saw up here, but for some epsilon, which is empty sequence, or the same loss function we saw up there, but evaluated with a API call that returns an empty sequence. Okay, so you can take this loss and you can either plug in an empty sequence, or you take that same loss and then you plug in an API call that returns an empty sequence. And one of those two is going to be lower than the other, and that's what this min here is doing. It's basically saying either this one or this one, whichever one of these two is lower, and that's going to be your li minus. So now you have this li plus, this kind of upper bound, and then this li minus. I don't know for sure if this is upper bound, lower bound, but that's kind of what I'm assuming they mean by these. The former is a weighted loss over all tokens if the API call and its result are given to M as a prefix. The latter is the minimum of the losses abstained from doing no API calls at all, and doing an API call but not providing the response. Okay, so this is another way of describing the minimum function that I just described there. Either doing no API call at all, which is this here, Li of epsilon, where epsilon is the empty sequence. and doing an API call but not providing the response. So here, this part here. Intuitively, an API call is helpful if 2M, the large language model, if providing it with both the input and the output of this call makes it easier for the model to predict future tokens, compared to not receiving the API call at all or receiving only its input. Giving a filtering threshold TF, okay, I think they introduced this threshold here. Sampling, okay, no, this is a different threshold. So they have a sampling threshold, which is where in the sentence are we going to put these API calls, and then they have a filtering threshold here, different threshold, tau sub f. Let's get rid of this one. We thus only keep API calls for which the difference is greater than tau. Okay, all right, this finally makes all the sense. Adding the API call and its result reduces the loss by at least tau f. Okay, so this is not an upper bound and a lower bound for the loss. That is not what the plus and the minus here mean. What's really happening is that they're using basically this up here, this loss, and then comparing it to the lower loss. So if the difference between these two losses is bigger than this threshold TF, and this threshold is just some number that they just picked, right? They experimentally determined what a good value for that would be. So they picked a value for that. If the difference between those two losses is greater than that threshold, then they're going to say this is a good API call, keep it here. So kind of reviewing what's happening here. They're using the large language model and they're giving it this prompt that's asking the large language model to put API calls inside a sequence of tokens here, this sentence. Then they're evaluating the language model at every single point along this sequence and saying, what is the probability that the next token is the start of an API call? And once they do that, they're going to basically have a probability for every point in the sequence that the start of the API call could be there, and they're going to pick the top K of those. And then for each of those, they're going to basically actually do the API call, but over different APIs, right? So they're going to have kind of like a classification style situation where you're going to have different API calls with different responses, right? And you're also going to be doing API calls with no responses, and then APIs that don't do anything, that are basically just an empty sequence. So when you do that, you can say, okay, well, I like the way that they describe it here. How helpful is this API call, right? This li plus here should be very different from this li minus, right? If the difference of this loss is small, which means that the API call with the correct API call with the correct response is not that much better than an empty API call or an API call with no response, then it means that that API call is probably not adding very much at all, right? Compared to not receiving the API call at all or receiving only its input. So if the difference here is very small, that means that that API call is largely worthless. If the difference between these two is very large, that means that the API call is adding a lot, so it is worth doing that API call. So that is how they go from a sentence into a sentence with API calls at the best possible places. All right, hope that was useful, maybe not. After sampling and filtering calls for all APIs, we finally merge the remaining API calls and interleave them with the original inputs. That is, for an input text x, x1 to xn, so they keep defining this. This is like the fourth time they've defined this text x with a corresponding API call. And result, at position, we construct a new sequence. We proceed, okay, so this is just, the new sequence is basically just the old sequence with the API call. You have x from 1 to I minus 1, then you have the API call, and then you have x from I to n. So they basically just put the API call in there. We proceed analogously for text with multiple API calls, doing this for all x in C. Okay, so C was the data set, remember? So all sentences within that data set, augmented with the API calls. We use this new data set to fine-tune M using a standard language modeling objective. Crucially, apart from the inserted API calls, the augmented dataset C star contains the exact same text as C, the original dataset. As a consequence, fine-tuning M on C exposes it to the same content as fine-tuning on C. Yeah, this seems like a little bit hand-wavy to me. Like they're just basically saying, hey, we take the original data set, we add these API calls, and then we train the LLM on this new data set with the API calls, and it should be fine. But I don't know how true that is, right? It's very difficult to evaluate that actual statement itself because it's very difficult to really know how, like, what an LLM is doing and like what the weights inside an LLM correspond to. So we don't really have the explainability when it comes to large language models to make this kind of statement, right? That if you expose it to the same content or largely the same content, it's going to result in the same model. So still don't know exactly what this is doing, but it obviously works in this particular example, in this particular paper, so it should be fine. Fine-tuning on C enables the language model to decide when and how to use which tool. When generating text with M after fine-tuning with our approach, we perform regular decoding until M produces the blank token, indicating that it next expects the response for an API call. At this point, we interrupt the decoding process, call the appropriate API to get a response, and continue the decoding process after inserting both the response and the API token. Okay. So basically, as soon as the model produces this arrow token, you're going to interrupt the model, right? It's performing inference. The model's sitting there and it's saying, what's the next token? What's the next token? What's the next token? What's the next token? If it suddenly says the next token is this arrow, it's going to stop what it's doing. It's going to call the API. It's going to get the answer to the API, and then it's going to put that response in there. So yeah, the key point here is that it's interrupting the decoding process, which is important because this is going to change the code, right? Normally, if you didn't have this interruption, your inference code, right, the code that is actually running when you have this model in inference mode, is going to be different. It's just going to be giving you next word, next word, next word, next word, next word, next word. But now you need to basically have an if statement inside your inference code that is saying, if this token appears, stop, call the API, possibly wait, possibly there's some timeout, and then put the answer. Yeah, and continue the decoding after inserting both the response and the API token. All right, we will explore a variety of tools to address different shortcomings of regular LMs. The only constraint we impose on these tools is that both their inputs and outputs can be represented as text sequences, and we can obtain a few demonstrations of their intended use. Concretely, we explore the following 5 tools: a question answering system, a Wikipedia search engine, a calculator, a calendar, a machine translation system. Okay, so these are 5 different quote-unquote APIs that they use. And the choice of these is pretty good, right? It's like calculator is like, this is always one that they talk about where LLMs just are not good at that. Like here, if we go to ChatGPT, so chat.openai.com, let's say, what is that plus that? It might not even know. This actually makes me think that it might be calling an API itself. Yeah. So I don't know, maybe OpenAI already has a calculator API call implemented. Some examples of potential calls and return strings for the API associated with each of these tools are shown in Table 1. We briefly discuss all tools below, and further details can be found. First tool is a question answering system based on another LM that can answer simple factoid questions. Okay, so actually one of the API calls is another language model itself, which is pretty crazy. Language model calls other language models. A language model teaches itself to call other language models. That's crazy. As a second tool, we use a calculator that can perform simple numeric calculations, so just basically calculator to confirm 4 basic arithmetic operations. Results are always rounded to 2 decimal places. If it's limited to the 4 basic arithmetic operations, I wonder what if I take the square root, or let's do a new one here. Let's do a new one. Let's do, what is log of 245 to the 34th power plus 56? $7.25. Oh shit, look at that. It's like breaking the log into little chunks. Yeah, but it doesn't actually answer it for you. It just turns it into code. Let's see if this is actually correct. No, it's not even correct. See that? Log of 245 to the 34th power plus 56 is not the same thing as 2 times log of 5 to the 34th power plus 56. So there's some mistake somewhere here. Our third tool is a search engine that, given a search term, returns a short text snippet from Wikipedia. So basically Wikipedia as a source of truth. As our search engine, we use a BM25 retriever. So this is 1995, 1999, kind of old school papers that index the Wikipedia dump. So this is basically the same level of like indexing technology that like classic Google search does, right? Where Google has scraped the whole internet, and when you type words into the Google search bar, it takes the search query that you have and it compares it to basically this giant database of the entire internet, and it's going to say, okay, what is the relevant information here? So it's like kind of, this problem is just called indexing, right? Indexing data, because you're finding the index at which a specific piece of data that you want exists. And this type of stuff has existed since the beginning of time, right? Even like the index in a book is a form of indexing, right? Like the very beginning of a book, like a table of contents, it's a search algorithm, right? Like you go into this book, you open the first page and you say, I want to go to chapter 10. And you can take that query, that chapter 10, and turn it into a page number by using that very first page, the table of content, which is basically an index algorithm. So there's obviously way more complicated versions of that, but the versions here, 1995, 1991, these are not deep learning based approaches, right? These are just classic search algorithms like the ones you would see in Google search. Although Google search at this point for some time now has had deep learning in it. Just not the large language model stuff. Although maybe at this point it does have large language model stuff in it. Our fourth tool is a machine learning translation system based on an LM that can translate a phrase from any language into English. Okay, so this is another LM language model. So the different tools that it's using here, right? So this paper is all about this language model using tools, which is basically just an API call. You have one of the tools is a calculator. The other tool is Wikipedia. The third tool here is a language model that answers questions, so a different language model. And then the fourth tool is a different type of language model that does translation, right? So this is a 600 million parameter translation model. that works for 200 languages. Let's make that blue. Blue is the color we use for like quantitative stuff like numbers. And the final fifth tool that it learns to use is a calendar API. Returns the current date to provide temporal context. Okay, so it has a calendar, it has a calculator, it has Wikipedia, it has a translator, and then it has a question answering language model. So that's pretty good. I mean, that's a pretty good choice of tools. Like if you thought about a human who had to perform the duties of something like a chat GPT, right? Like what would you want to give that human access to? I think this set of 5 tools is a pretty good set of tools, right? You give it Wikipedia so it can search Wikipedia if it needs to. It has a calculator, it has a calendar, and then it has a translation machine, and it has a simple question answering machine. I don't know why, to me this is kind of the weirdest one. Like, why does it need this question answering? Right, like shouldn't the base language model be good enough to answer these? Like, I'd be curious if they do an ablation study, like how much this one adds. We investigate whether our approach enables a model to use tools without any further supervision and to decide for itself when and how to call which of the available tools. To test this, we select a variety of downstream tasks where we assume at least one of the considered tools to be useful and evaluate performance in zero-shot settings. Okay, so they're not going to be fine-tuning the LLM for specific tasks. That's kind of their whole point, is that they can use a generic LLM, and just by training it to use tools, it can hopefully perform well in these tasks that are going to test it on things that are generally hard for LLMs, such as probably math. I almost guarantee you there's going to be a math one here. We also ensure that our approach does not hurt the model's core language by verifying at perplexity on 2 language modeling datasets. So perplexity is kind of a measure of confidence. Let's get you guys the official definition here. Perplexity, not a startup. Perplexity in the context of AI in LLMs. Perplexity is a measure of how well a language model predicts a given test set of text data and is calculated as the exponential average of the model's prediction errors. So let's actually see what ChatGPT has to say. What does perplexity mean in the context of LLMs? Do you have perplexity? Let's see if ChatGPT is self-aware. In the context of language models, perplexity is a measure of how well a model predicts the likelihood of a sequence of words. Right, so likelihood is basically kind of like a probability. You could think of it that way. It is used as a way to evaluate a model's ability to generate coherent and grammatically correct sentence. Perplexity is calculated as the exponential of the cross-entropy loss of the model over a set of text data, and it provides a single scalar number that summarizes how well the model fits the data. A lower perplexity score indicates that the model is making more confident predictions and therefore better fit. Yeah, so low perplexity, more confident. Seems like bullshit. I don't have a perplexity score in the traditional sense, as I am not a traditional probabilistic language model that assigns probabilities to individual tokens. Isn't that exactly what you do? I use deep neural networks to generate text based on the pattern I've seen in data on the I was trained on. That's exactly what you're doing. Probabilistic language model that assigns probabilities to individual tokens. Generate text based on the patterns I've seen in the data. That's kind of weird. It's not self-aware. Oh no. Throughout all of our experiments, we use a subset of CCNet as our language modeling dataset, C and GPTJ. Okay, so this is the dataset, CCNet. I think red is the color we're using for data. And then GPTJ is the actual language model that they're using. To reduce the computational cost of annotating C with API calls, we define heuristics for some API calls to get a subset of C for which API calls are more likely to be helpful than for an average text. Okay, so they're not doing their whole this approach here that we explored this like sampling and choosing where to put the API calls and then filtering those API calls on the ones that are most useful. They're not doing that for the entire data set. They're only doing that for a subset of the data set here, which they say they're using some heuristics, but we only consider text for the calculator tool if they contain at least 3 numbers. So basically, it seems like what they're doing is like they're going to filter it based on these human rules, right? Heuristics. Every time you see heuristic, just think of it as like a human-defined rule. Usually, you can have non-human defined heuristics, but almost always it means basically there's a human in the loop. And here, what they said is, okay, if for any text in the data set that has at least 3 numbers, we're going to create a augmented API call math data set with that. Okay. Why don't we actually, so we didn't actually look at these figures. We looked at this figure, but we didn't look at this figure. This one is figure 2. Key steps in our approach illustrated for a question answering tool. Give it an input text T, so this is the text. XI to I minus 1. Pittsburgh is also known as the Steel City, so this is, right, I is the position at which you're going to insert the API call, so this is the beginning of the sequence, right before the API call, and then this is the second part of the sequence after the API call. So first thing here is you're picking where in the sequence to insert the API call. Then you're going to sample a bunch of different API calls, right? So here's one. What is another name that Pittsburgh is known by? Which country is Pittsburgh in? You're going to execute those API calls, right? You're going to use that little arrow token, and then after you put that arrow token, you're going to get a response, and you're going to put the token for that in there. And then you're going to say, okay, now I have a sentence with no API call. I have a sentence with this API call and this response. I have a sentence with this API call and a null response, right? This one here and this one here. And then I have an API call with this correct response. So basically 3 different things. You have the sentence with nothing in there, or the sentence with basically a null call, the sentence with the API call and a null return, and then the sentence with the API call and the real return. And if the difference between those 3 loss functions, right, is within some threshold, then you're going to say, okay, this API call with this specific response was actually useful for this sentence, so we're going to keep that. All right, and you see here, this is what the less than and the greater than. So I guess in this case, the API call with the answer was not, the loss function for that was not really smaller than the loss function for this, which means that the API call really didn't help that much. We execute these API calls and filter out all the calls which do not reduce the loss li over the next tokens. All the remaining API calls are interleaved with the original text, resulting in a new text x star. And then here, I guess, figure 1, which we skipped over, but we might as well just look at it now. Example predictions for Toolformer. The model autonomously decides to call different APIs. Interesting use of the word autonomously here. The model has been trained on API datasets to obtain information. So these are all the different tools. So you have the math tool here, calculator. You have the translator. So this is another LLM. This is an API that itself is an LLM. You have the QA. This is also a large language model. So the large language model is calling another large language model to answer this question. You have Wikipedia here. So the large language model is using Wikipedia via API to get this here. So you have large language models calling other large language models, or large language models using simple tools such as a calculator, Wikipedia, and I think they also have a calendar. So that's where we're at. Now let's go back down. Okay, so we were here. Blah, 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 details for the heuristics. For obtaining C star from C. So the C star is the augmented data set, C is the original data set that the language model was trained on. We additionally filter out all examples for which all API calls were eliminated in the filtering step. So, okay, they're only using API calls that are past a certain threshold. For the weighting function, this is the weights for each of the different possible API calls. Okay, so it's the sum of all weights, where here you have the sum of all weights over S, where S is, I guess, I don't know, what is S? Maybe all sequences? Oh no, S is the sample. So all sampling points, you have the weight for each of those sampling points. You have TS is again the sampling threshold, and then TF is the filtering threshold. So you have two different thresholds here. And actually, not only is each of those a hyperparameter, but you have a different threshold for each tool. So if there's 5 tools, there's going to be 10 total thresholds. And each one of those is hand-tuned. So that's not necessarily great. That's a lot of hyperparameters for something like this. Ideally, you'd be able to figure out some way to not have these hyperparameters here, these additional thresholds that you have to hand tune. Yeah, because even look here, like this is very hand designed. 1 minus 0.2 times t. You know, like what the fuck is that? You know, here's a bunch of random human design numbers too. So yeah, maybe future work would be to kind of figure out a way to get rid of these thresholds and not have all these like hand-tuned weights with these special max and min functions. Okay, fine-tuning. So once you actually create this augmented data set with the API calls, you want to fine-tune your language model on that augmented data set. So this is what they're describing here. They're tuning with a batch size of 128 and a learning rate of 10 to the negative 5. With linear warm-up. So warm-up here, right, when you're training models, a lot of the, for example, optimizers that you use have momentum terms, and a lot of the regularizations that you do, such as batch norm or layer norm, also have some kind of like hyperparameters and kind of momentum-like terms within them, right? You might even be doing kind of averaging on your weights. So all these different little tricks that people have used and developed over time to train deep learning models in a more stable, in a faster and more efficient way. They usually require some time to kind of get warmed up, right? So basically the momentum term in your optimizer, you might have to take a couple gradient steps before it has a good kind of momentum. So when you're training a deep learning model, what a lot of people will do is they'll have this warm-up period, right, which is the first 10% of the training. And during that warm-up period, you're not actually pushing gradients into the model. You're not actually training the model. What you're doing is you're basically going through the motions as if you were training the model and really only updating the kind of momentum terms for your optimizer, or maybe the averages that you're using in your different normalizations and regularizations. So that's what the warm-up period here means. Throughout the remainder of this section, we mainly compare the following models. Okay, so this assumption is empirically validated. They did perform the ablation study to determine if fine-tuning on a modified data set wouldn't mess with the original language model. Okay, these are different models that they try. So GPT-J is the original pre-trained large language model. GPT-J plus CC. Okay, so this is the same model but fine-tuned on the data set without any API calls. Toolformer, which is GPT-J fine-tuned on the data set with API calls. and then Toolformer disabled, which is the same model, but API calls are disabled. Okay. So basically regular model with fine-tuned, no API calls, regular model fine-tuned with API calls, and then regular model fine-tuned, but the API calls return none. Or I guess they're removed or something like that. We additionally compare to OPT, so they have some baselines to other transformers here, or other large language models, GPT-3 and OPT. API name, example input, example output. Examples of inputs and outputs for all APIs used. So you have, there are 5 different APIs, right? The 5 different tools. API in this paper is basically the tool that they're using. So for example, in a calculator, the calculator API, which is the calculator tool, you might have an input which is 27 plus 4 times 2. And the output for that would be 35. Machine translation, sûreté nucléaire, nuclear safety. Okay, so this is just the API. So this is not the large language model, right? This is just each individual tool is a function itself, right? And if you give the calculator this, it'll output that. And it's important to note that actually some of these tools are large language models themselves. So specifically the question answering and the machine translation tools are themselves large language models. Okay, downstream tasks. We evaluate all models on a variety of downstream tasks. In all cases, we consider a prompted zero-shot setup, i.e. the models are instructed to solve each task in natural language, but we do not provide any in-context examples. Interesting. Where models are provided with dataset-specific examples on how a tool can be used to solve a concrete task. We choose the more challenging zero-shot. So zero-shot basically means that you're taking your first shot at the 0th step. That's like one way to think about it. But it basically means just trying something without fine-tuning on that something. So zero-shot classification would be taking your model, which has not been trained at all on a specific classification task, and seeing how it performs on a classification task that it has never seen before, right? Zero shot. So the 0 there just basically means there's 0 fine-tuning, 0 additional training, 0 task-specific modification of your model. Right. They want to see whether Toolformer works precisely in those cases where a user does not specify in advance which tool should be used in which way for solving a specific problem. We use a standard greedy decoding, which basically just means the highest probability token. But with one modification, we let the model start an API call not just when API is the most likely, but whenever it is one of the k most likely. Okay, so when they're actually doing this zero-shot task, right? They have their large language model with they've trained. They're going to do it for each of these 4, but we're going to assume that it's the one that actually does something, the Toolformer. And it's going to start reading your sentence token by token. And it's going to start crafting the response, right? And it's going to start crafting the response token by token as a large language model does. And as it crafts the response, it's going to be doing standard greedy decoding, which means that it's always going to pick the highest probability token when calculating the next token in the response. But what they're going to do is every time it predicts the next token, they're going to make it predict the next k tokens, and they're going to say, or the next, not the next k tokens, but the k possible tokens that would be the highest probability to be the next token. And they're going to say, if the API call token, right, this API in little, what is this, triangle brackets? Carets? If the API call is one of the top 10, then we're going to basically call the API. So the sampling when they were doing the actual augmentation of the data set, had a specific threshold, but you can't use that threshold when you're actually performing inference. So when you're performing inference, they have a different hard-coded hyperparameter. It's not a threshold in this case. It's instead going to be a K here, which is like a top 1, top 5, top 10, but they could have picked top 7. They could have picked top 100, right? So at the end of the day, this number here is also hard-coded. It's picked by a human. So not only do they have thresholds for each of the different tools, but now they also have this K most likely number that is probably picked for each tool as well. Maybe not. Maybe they use this K equals 10 for all of them, but we'll see. At the same time, we only at most one API call per input to make sure the model does not get stuck. This is wrong English here. Llama, we evaluate our models on the squad, GoogleRe, and TReX subsets of the Llama benchmark. Okay, so this is the actual tasks that they're going to be zero shot on. Okay, the task is to complete a short statement with a missing fact. Llama was originally designed to evaluate masked language models. We filter out examples where the mask token is not the final token. Okay, so mask prediction is basically predicting. You could think of it like you have a sentence and then one of the words in the sentence is removed and you have to predict what the word inside the sentence was. But the language model that they're using here, it doesn't work like that. It predicts the next token given the beginning part of a sequence. So what they're going to do is they're going to filter out any examples where the mask token is not just the very last token. Okay, so they're already messing with this benchmark. I don't like this. I don't like the fact that they took this benchmark and then they filtered out specific. They filtered out only a subset of the benchmark and then changed the actual evaluation criterion. And then here they do basically like a top 5 accuracy. As Llama is based on statements obtained directly from Wikipedia, we prevent Toolformer from using Wikipedia's search API to avoid giving it an unfair advantage. I mean, I don't know. That seems like you should just do that and then just be like, look how much better our model is. Okay. It outperforms the big models, OPT and GPT-3. Same thing. They're going to basically do the same thing for math. This one's probably going to be even more crazy. So these are the different math benchmarks that they chose to use. Okay. While GPT-J and GPT-J-CC perform about the same, Toolformer achieves stronger results. Yeah, actually, this sentence here makes me dubious, right? Like, they said it here. They're like, while this filtering alters the distribution of training examples, we assume that the remaining examples are close enough to the original distribution so that M's language modeling abilities remain unaffected, right? They made this assumption here, which we called them out for, where we said, hey, if you retrain the language model on a modified data set, that's not the same language model anymore, right? This assumption that they made here, fine-tuning M on C star exposes it to the same context as content as fine-tuning on C. And we were like, hey, I don't think it's necessarily the same thing. And here, this is what they're saying. It's, okay, the one that's been fine-tuned on the subset and not the subset perform about the same. But to me, it's like, what does about the same mean, right? Like, is that a valid evaluation of like the model being the same? I don't know. Seems to me like maybe not. Maybe the model changed a little bit by having all those API calls in there. Okay. Allowing the model to make API calls more than doubles performance for all tasks. Yeah, it's going to be just way better. So let's see how bad GPT-3 is at math. So these are the math benchmarks here, this table. Sorry, I'll scroll up. My head is probably in the way. So these are the math benchmarks. So we see GPT-3 is at 14, 10, 19. These are pretty shitty numbers compared to these numbers here. 29, 40, 44. So this is the actual full model that has the API calls. It can actually use a calculator. This is the model without the API call. So interesting that even without the API call, it gets a better performance than just the model as is, right? So if the model has like fake API calls that don't actually return anything, it somehow ends up more accurate than the one that doesn't have the API calls at all, right? And this is like an interesting property of language models where humans don't understand how to create context that makes language models more performant. It's kind of like how sometimes there's all kinds of tricks that people will have, right? Like if we put here, for example, let's think step by step, right? You would think as a human, your intuition is that the question is the question and it doesn't matter. But when you add different context, right, and there might be like some fake API call. So like, I don't know, maybe we could say explain sentence. So we're going to wrap this sentence in a fake API call. A equals that, print A. So we're asking the same exact question, but we're now like prompt engineering it into a fake API call that has absolutely no meaning. Like this is just a random function in Python like type thing that I just defined here. And if we do this, is this a different answer? I don't really remember anymore, but like you're messing with the model, right? By changing the context, you're going to change the actual answer, even though largely the thing is the same. So you see how it actually gave us a shorter one. So that's kind of what I'm showing you here, is that this 7.5 and this 14.8, this one doesn't have any tools. It just fakes the API calls. It just basically writes the API calls, but then nothing happens. So even with the API calls to a calculator where nothing happens, it somehow gets higher performance than the one that doesn't get access to that, which is kind of crazy. Okay, then they have question answering. Blah, blah, blah. It's good at question answering as well. Interesting. The Toolformer is not as good as GPT-3. But also because the question answering model that it's, the question answering tool that it's using is itself also a large language model, so it would make sense that the huge large language model like GPT-3 would just be better than both of those combined. And then multilingual question answering, so this is the translating one. They're still kind of doing these like hand designed benchmarks, but I think at least they're using that for the GPT-3 as well. So API calls, blah, blah, blah. Mainly because for some languages, fine-tuning deteriorates performance. OPT and GPT-3 perform surprisingly weak across all languages. What happens if you give ChatGPT a ¿Qué me puedes explicar? Can you explain to me perplexity in the context of LM? So it's like this is like half the sentence is in Spanish, half the sentence is in English. Let's see what it says. Damn, it just took it right in stride. It just didn't even care. That's interesting. What if I change this to perplexidad? I don't know how to spell perplexity in LLMs. There you go. La perplexidad en modelos de lenguaje de aprendizaje de máquina. Look at that. This is LLMs in Spanish. Modelos de lenguaje de aprendizaje de máquina. Se refiere a una medida de la incertidumbre. Okay, so that's pretty good. If you do the first part in Spanish, second part in English, it answers in English. If you do all of it in Spanish, it answers it in Spanish. So it's quite good. Potential reason for GPT-J not suffering this problem, blah, blah, blah. We also evaluate GPT-3. GPT-3 performs better than all other models. Okay, so let's see here. This is the question answering, and then this is the translation. So question answering, GPT-3 is actually better. So that's kind of a fail here for Toolformer. So Toolformer, using another language model as a tool. So this is Toolformer, which is a language model with this little helper buddy, which is also a language model, can't beat GPT-3, which makes sense. GPT-3 is just bigger than both of those, Toolformer and its little question answering buddy themselves, so it makes sense that GPT-3 is going to be better than that. On translation, you see kind of a similar situation here. So translation, I think ES is Estonian? Oh no, Spanish. Español. Toolformer performs quite well. GPT-3 performs quite poorly, but then if you have the version of GPT-3 that basically has supports all languages, then GPT-3 is actually better. Interesting here, the vanilla version of GPT-3 is actually way better on Chinese, Zhongguo, than it is in Spanish. Much better on Zhongwen, I think. Zhongwen is Chinese in Chinese. To investigate the calendar API's utility, we evaluate all models. Okay, so now they have the final benchmark, which is the calendar, kind of like time-based questions. Temp llama that contains close queries about facts that change with time. Is this a typo? What the fuck is a close query? A closed test is an exercise consisting of a portion with items removed. Huh. I had never heard that term before. So close is basically just to fill out the blank. I would just call it masked. But there you go, and learn something new every day. Close means fill in the blank. Dataset described in Appendix D is also generated through a series of templates, but populated using a combination of random dates and durations. The Toolformer outperforms all baselines. Of course, it's going to be good at this one. So here we go. And it's just barely beating the GPT on temp llama, but this one here, date set, it's way better, which is interesting. Okay. Okay, so actually this temp llama baseline, or not baseline, this 10 llama benchmark, which is the one where it barely beats GPT-3, it's actually mostly using Wikipedia search. It's not really using the calendar tool. So it's choosing to use the Wikipedia tool. But dateset, which is the other benchmark, or the other benchmark for time stuff that they're deciding for on here on this paper, it does end up using the calendar tool. So it uses the calendar tool 54% of the time. So I don't know what dateset is, but I'm assuming it's like, what is 6 months away from like January 12th, 1934 or something like that. It's like weird like text questions about like doing calendar math. So it's like effectively just like a calendar calculator. Language modeling. In addition to verifying improved performance, we also want to ensure that language modeling performance does not degrade through our fine-tuning task. Yeah. Or fine-tuning process. So this is the kind of part that we've been suspicious about this whole stream, is whether or not it actually does mess with the language model to fine-tune it on the data set it was trained on, but with all these additional API calls. Like, how much is that messing with the actual transformer? So the way that they're going to test that is they're going to evaluate their model on 2 language modeling data sets. So they're going to have they have wiki text here, which I assume is probably just Wikipedia text, and then a subset of the CCNet. So this is the one that they were fine-tuning on anyways. Not used in training, so maybe like a validation set, some holdout set. It slightly deteriorates performance on wiki text. Okay. So even though it slightly deteriorates performance, which I would say is indicative that something happened and the large language model has kind of been fundamentally changed by being fine-tuned on this API augmented data set, they say that, hey, even though it changed and the numbers aren't necessarily the same and the performance is different, the perplexity, right, which we know is basically just a measure of confidence, just like how confident is your model in these predictions when it's producing wiki text, right? So it's basically going and trying to like recreate the text on wiki text, and each time it predicts a token, it has some probability score, and then from those you can effectively boil them down to a perplexity, which is like over this generation of wiki text, how confident was it every time it generated these tokens. And lower does not lead to an increase in perplexity compared to training on C. So you can see here how this is GPTJ and then GPTJ plus CC, so plus the fine tuning. So I guess actually we're mostly comparing these here. And these numbers are very close. So it's changing it, but it's not necessarily making it worse, as long as your definition of making it worse is that the perplexity on wiki text is about the same. Hard to say. I think this is more and more going to be a theme in the future, and specifically in the field of like machine learning, is you're going to see people take these large language models and fine-tune them on things and give them specific tools, give them all these additional things, like give them different heads. And like, we already don't understand how these large language models are really understanding and storing information, right? We don't really understand what is going on inside the black box of the weights of this neural network that is the transform, or that is the large language model. So I think it's going to be a huge area of research in determining the impact that fine-tuning has on large language models. Like if I take my large language model and I fine tune it on cooking data, how much worse is it now on landmark tasks or something like that? Like what is that trade-off, right? And I think part of the reason we're not necessarily very good at answering that question is that our benchmarks just aren't that good, right? It's like, what does a low perplexity or a high perplexity when you're auto-completing wiki text mean? Is that a good like analysis? Is that a good quantitative way to measure your LLM? Like, do you eventually have a world where you have different wiki texts for different types of tasks, and that's what you're doing? Like, it just seems like an interesting research direction to find or create better benchmarks for different tech or different tasks, such that we can measure the generality of a large language model more quantitatively. And this is me as a computer vision person being a little bit ignorant that there's probably a bunch of people that do research on this, right? There's probably a bunch of researchers that do have been doing this for large language models for years, and I'm just sitting here postulating the research that they've been doing. Okay. To this end, we apply our approach to not just GPT-J, but also force models. Okay, so here they're going to be doing the size ablation. So all the results that we saw here was with a 1.6 billion parameter model, and now they're going to basically try to do it with smaller models. So everything from 124 million parameters to the 1.6 billion parameters. They're only going to be doing it for 3 different ones here: question answering, calculator, and Wikipedia. Smaller models achieve similar performance with and without tools. Okay, the models become better at solving tasks without API calls as they grow in task. Their abilities to make good use of provided API improves at the same time. Okay, so this is kind of interesting because, right, one of the things that current large language models in the form of like ChatGPT have an issue with is that you have to perform inference. Every time I type a question here, right, I have to perform inference on this large language model, which is probably kind of expensive, right? It's a big language model that knows everything and has been trained on a huge amount of data. But wouldn't it be a lot more efficient and a lot less computation if instead there was a much smaller language model that all it did was it basically looked at your question and said, okay, I'm going to guess that the LLM that you really want to use is this one here. It's this cooking LLM or something like that, right? So I could see a future where you have smaller models, smaller language models that you interact with, and those smaller language models are kind of like a librarian, right? They just kind of point you to a different kind of language model, which is bigger and is specific to a specific task. And that is a way of kind of reducing the overall compute use when you're interacting with an AI. So that's something they're kind of like hinting at here, and I could definitely see that being the case where you don't actually interact with the large version of the LLM whenever you're interacting with it like this. You're basically interacting with small versions of the LLM, and then there's large versions for different subtasks, and then the little LLM just knows when to ask the big LLMs for help. But they do say here that the little LLMs are not as good at asking for help, right? They don't know when to query the API as well as the big LLMs. So the big LLMs are better at knowing when to ask the API. Okay. They investigate the effect of the modified decoding strategy, where instead of always generating the most likely token, we generate the API token if it is one of the K most likely tokens. So this is the kind of hard coding thing they had where they picked, yeah, so here you go. So they had this K, right? How did they pick this K? So, well, they just did an experiment and they did it with different values of K. So they have K 0, 1, 3, and 10. and it looks like k equals 10 is the best. But not even. Look at this. Like sometimes k equals 3 is better. So this kind of goes to show you that it kind of sucks to have to hand pick these numbers, right? As a human, it'd be great if you could formulate the problem in such a way that you didn't have to be hand picking these numbers such as k. Performance for different values of k. Increasing k leads to the model doing API calls more often. For k equals 1, the model is calibrated. It decides to call APIs for examples that it would perform particularly badly on without making the API calls. Yeah, so there's a kind of a trade-off here, right? Do you want it to be very eager to call the API and eager to call wolf? Or do you want it to only call wolf when it like 100% knows that it has no idea what's going on here? So this is interesting here. So maybe k is not necessarily a negative. It's not a negative that you have to pick it, right? It's actually a positive because as the human, you kind of get to define how the final language model should behave, right? Do you want a language model that is very eager to like fact check itself, or do you want a language model that is kind of a little bit more confident and doesn't fact check itself very often? So I like whenever people take a hyperparameter that has to be picked by a human and instead expose it to the human that's interacting with the AI so that the human can tune it, right? I think that's a good way to modulate and change the behavior of these language models, is expose some of these parameters here. I think, for example, another one that is very common is in diffusion models. There's this conditioning, like kind of guidance weight, as it's called, where it's basically you can choose how strong you want to condition the generation of an image to a specific text or some class token or something like that. So just another little knob to give to the human so that they can interact with the AI that they want to interact with. Hello. Mugen. We qualitatively analyze some API calls generated with our approach for different APIs. Okay, as the model can be seen, high values typically correspond to useful API calls, whereas low values correspond to API calls that do not provide any information. Some amount of noise in the API calls that are not filtered can actually be useful, as it forces the model fine-tuned on C to not always blindly follow the results of each call it makes. Okay, maybe. All right, let's look at these figures here. So average performance on Llama and our QA benchmarks. Okay, so this is the question answering task and then the math task. So these are different benchmarks, different tasks. GPT-3, this is the performance of GPT-3 shown as a dotted line. Model parameters, this is the size of the model. So actually this line is incorrect. This dotted GPT-3 line, GPT-3 itself also comes in different sizes. So there should also be different, this dotted GPT-3 line should actually also be a plot itself. This should also be a line, right? I feel for this chart to be correct, they should have basically shown you GPT-3 at different sizes. But here they just show you the performance of GPT-3 as if it was just a single size. But largely, kind of here, these plots are what you would expect, where the smaller models, right, the smaller versions of Toolformer and the smaller versions of Toolformer, which does not have disabled, basically means it doesn't have the API calls. You can see the bigger the model is, the better the performance, which is pretty par for the course And I guess what they're showing here is that larger models learn how to make good use of them. That very small models, right? The with and without the API, it's largely the same. It's like mostly garbage. But then as your model gets bigger, the with and without the API actually makes more and more of a difference, which means that the language model is actually effectively using the tool. It's effectively using the API to get a bigger score. And another thing to note here is that on Llama, which I think is the... What is Llama? Is Llama the... Yeah, Llama is the dates. So it's like calendar events. It's like guessing calendar events correctly. So you can see here that the calendar events and the math are the difference between having an API, having that tool, and not having that tool is huge, right? The language model is way better at answering calendar and math questions if it has access to the API that corresponds to a calculator and a calendar tool. But when it comes to answering QA questions, right, the language model, the tool that it's given access to in this paper is just another language model. So the difference between a large language model trying to answer QA questions and a large language model trying to answer QA questions that has access to another language model that also answers QA question, that difference is actually quite small. So that's another thing to notice here, is that for things like math and calendar, it's more effective to use a tool versus in a QA benchmark, you're not necessarily doing much. You might be better off just asking the language model directly, which is what you're seeing here, right? ChatGPT or GPT-3 is actually much better at QA than these smaller models that have an access to tools. Okay, so language model pre-training here, they're going to go through some related works. Okay. Additional information is always provided. Okay, sure. Tool use, here's a bunch of papers where LLMs use the ability to use external tools. So yeah, this paper is not necessarily novel or unique in that. Like you can see here, there's a lot of work. A lot of it is recent, 2022, 2021. This is something that people have really started to kind of ramp up on, right? Everything from web browsers, calculators, translation systems. So like, the fact that language models can use all these different tools, like, I don't know, to me, that's evidence that means they passed the threshold of AGI, you know? They're a general intelligence. Look at this. Anything that can use a Python translation system, a calculator, web browser, like, I don't know, I think we're there. I think low-key the world we've already gotten past the point where language models or AI has gotten smarter than humans. Maybe not smarter, it's still like a little dumb human, but like we're there, you know? Haters be haters. I'm 100% on team. We're already there. In contrast, self-supervised nature of Toolformer enables it to learn how and when to use tools without requiring a specific prompt that shows task-specific examples. Yeah, I would say that you still need to tune those thresholds, so there's a little bit of hand tuning and expertise required. This wouldn't necessarily just work for any API tool. Okay, using self-training and bootstrapping to improve models has been investigated in various contexts, so other people have kind of done similar type things. Few-shot text classification, reasoning. Toolformer is trained on its own predictions after adding a perplexity-based filtering step. Our approach enables LMs to learn how to use a variety of tools in a self-supervised way. There are some clear limitations on what can be achieved with our method in its current form. One such limitation is the inability of Toolformer to use tools in a chain, using the output of one tool as an input to another tool. I mean, I don't think this necessarily matters. I feel like any API can be combined with another API to create a new API. So I think chaining tools together seems like a kind of obvious next step and not too much of a reach. Our current approach does not allow the LM to use the tool in an interactive way. Yeah, this is a little bit more the complicated, where you could you almost have to start framing this as a reinforcement learning problem with an agent that takes actions in order to kind of use a tool interactively. We found models trained with Toolformer to often be sensitive to the exact wording of their input. I feel like this is true for all language models and this is really the field of prompt engineering, where, hey, you have to be very careful about specifically how you type in questions because the language model is very sensitive to context. Our method is very sample inefficient. Yeah, processing more than 1 million documents and only a few thousand examples of useful calls to the calculator. I would say this is because of the threshold thing, and the heuristics that they use to filter down the data set. So yeah, they say maybe if they iteratively applied it, they would be better at kind of picking examples that are worth augmenting. Okay, and then finally, deciding whether or not to make an API call. Toolformer does not take into account the tool-dependent computational cost incurred for making an API call. So when ChatGPT gives you an answer, right, it's performing inference and it's like kind of putting out word by word. But imagine if it was this Toolformer and it got to here and then it wanted to do an API call. It would actually have to pause, perform the API call, get the request back, put it in there, and then continue to do it. So you could see how if you wanted to generate a paragraph and the paragraph had 10 different API calls in it, now it's going to be a lot slower because it has to perform 10 external API calls. So I think for these types of little things like calculators and stuff like that, it seems fine, but I could imagine a world where eventually the APIs that it's using have a high computational cost, and so you have to be more careful about whether or not it's worth making that API call. Language model that learns in a self-supervised way. How to use different tools such as search engines, calculators, and translation systems. This is done by fine-tuning on a large number of sampled API calls that are filtered based on whether they reduce perplexity on future tokens. Toolformer considerably improves zero-shot performance of a 6.7 billion parameter GPT-J model, enabling it to even outperform a much larger GPT-3 model on a range of downstream tasks. Yeah, so relatively simple idea, and it's not necessarily a new idea, right? They do admit that, hey, there's a ton of different people who've been doing this for a bunch of different things, right? Tool use, there's a bunch of different tool use papers for LLMs, but I think it's really, I don't know what to say here. I'm just I'm still amazed that you can do this, right? That we can take an LLM and literally ask the LLM, use the LLM to label a data set or augment a data set with API calls, and then fine-tune the LLM on that data set, which it created itself. And that data set that it created itself and then you're then fine-tuning on tells it to question another LLM, which is specifically fine-tuned for question answering. So it's the levels of different LLMs here, forming a more complicated system where you have multiple LLMs being called. I think this is indicative to me of where natural language NLP research and NLP AI is going. I think as you see these language models be productized into things like ChatGPT and Bard from Google, the complexity of these different types of systems where you have different sizes of language models, that are fine-tuned for specific things, that can call external APIs that are basically all other LLMs. So you have like many different LLMs like all calling each other in these complicated webs of like when to use the question answering LLM, when to use a calculator, when to use the machine translation LLM. So I think this is going to be kind of where a lot of people spend a lot of time in the next 5 years, is like kind of in the productization of language models, figuring out these like kind of complicated systems like this where you have a lot of different LLMs to give you one clean experience that produces the best possible responses. It's interesting for sure. Yeah, that was that. That was Toolformer. Hope you found that interesting. Feel free to join the Discord and ask questions. If not, like and subscribe, and see everybody